Hey everyone, this is Jana Stafford with BIC Magazine. Welcome to our webinar, Transforming Inspections, the Role of Robotics and Pulsed Eddy Current NDT. Before we get started, I'd like to give first a few quick pointers regarding your desktop webinar console. Our presenter's webcam will appear in the media player window, which is in the upper right corner, but could look a little bit different on your mobile. And you can resize the media player and the slide window if you like. At the bottom of your screen, you'll see a few useful widgets. There's a Q&A widget to type in questions at any time during the presentation, but the Q&A will occur toward the end. The Peach widget is where you'll find contact info for our presenters, and there are a few other more self-explanatory widgets that you may want to check out. Our webinar today is sponsored by Erix Technologies. Erix was founded by industry veterans collaborating with skilled robotics engineers and data scientists. From the beginning, the company's focus has been to help solve the biggest pipe corrosion challenges plaguing its customers and the energy industry as a whole by bringing together industry expertise and technical innovation to improve safety performance and cost effectiveness. For today's webinar, I'd like to introduce Tyler Flanagan. Tyler brings over 15 years of invaluable leadership experience in the field of NDT. He's a heavily certified and highly skilled NDT technician with a comprehensive understanding of industry standards and practices, demonstrating versatility and proficiency in managing complex projects within the oil and gas and energy sector. Next, I'd like to introduce Donald Picard. Donald has worked more than 10 years on the improvement of electrodes used for the primary aluminum production, in which he developed a strong expertise in material characterization using NDT techniques. Donald joined Eddy Technologies in 2020 as an applications expert and has since worked with the surface applications team in the development of custom eddy current solutions with a focus on the oil and gas and power generations industry. And I'll now hand the mic over to Tyler to kick us off.
Hello, everybody. I hope you're all doing well. Today, we're going to discuss and go through a bit of industry background specific to the oil and gas industry, corrosion and some of its challenges, conventional inspection methods. Donald's going to go into a little bit of a technical dive into an intro into pulsed eddy current, and then we'll circle back and discuss the benefits of integrating these methods into robotics. So starting off, refinery demand. In the United States, refining capacity exceeds 18 million barrels of product a day. So that's at its peak, absolute max, 18 million barrels a day. That's a lot. Over the last 6 years, the US has consistently increased its production of crude oil, reaching almost 13 million barrels a day. So there's been no country in the history of the planet that's been able to pull crude oil out of the ground as fast as the United States over that span. So it's very impressive. Even though we're in this phase or this transition within energy, there's still the demand and there's still the projection of increased and continued growth. So with the demand as high as it currently is and what it's projected to be, the number of inspections is going to be on the rise. Asset integrity and inspection programs are under extreme pressure. I know they typically are, and they always will be, but especially with the increase in production, the pressures these programs are under are to reduce risk, improve safety and reliability, all while lowering costs. So production is going up, but we need to cut costs. These programs are essential to maintain safety, regulatory compliance, and productivity. So in order to maintain that production that we've been having, these programs are crucial to achieve these numbers. Aging plants and corrosion, well, we all know most of these plants weren't built yesterday. They're decades old, most of them. So, and with decades old plants and refineries, different sites, that equipment is decades old and subject to different mechanisms of damage or to deterioration. Some of the main corrosion issues with these aging plants, there's safety concerns, there's operational disruptions, there's environmental risks, there's financial implications. So repair costs, production losses, regulatory penalties. An unbelievable statistic here. It's mind-boggling. The annual cost of corrosion in the United States across all industries, $276 billion a year with a B, 276 billion. That's all industry, sure, but that's the impact corrosion has. And what it does is it's really the impact it has on operations, the impact it has on production and maintenance is unbelievable. So when trying to locate areas of corrosion for maintenance, a high degree of clarity is extremely important. This necessitates an understanding of the scale and the magnitude of corrosion on any given point in your piping systems and your equipment. So what does this mean? Well, being able to identify and assess corrosion before it becomes widespread and disruptive. So we want to avoid having to shut down a piece of equipment. You're able to save money by focusing on preventative maintenance rather than spending money on post-damage repair. So it's more of a triage effect. You're able to focus efforts and manpower and money towards certain areas instead of kind of randomly and sporadically checking. You know where to target and where to spend your money. So it's very important. In terms of conventional inspection challenges, there's a handful. There's a lot. Safety's probably one of the most important. To perform many inspections in a plant at a site, access to difficult to reach locations or equipment is mandatory. There's no way around it. You have to gain access to a piece of equipment. So whether it's working at heights, you could be in confined spaces, you could be in hazardous areas, there's toxic chemicals and there's explosive gases. There's all kinds of situations that you have to be in to inspect equipment or could be in. They have to be accessed in some way, shape, or form. It is what it is. They are where they are. There's other challenges posed as well. Mostly, aside from the safety piece, there's also high costs, labor-intensive work, incomplete inspection data, and then analysis limitations. So the costly and labor-intensive aspect, well, that has to do with access. It's all about access. So if you're having to access a potentially hazardous area or be exposed to a lot of risk, the price could go up. And that could also limit how much data you can collect dependent on where the risk involved and the actual access to that piece of equipment. So addressing the complexities of corrosion inspection involves overcoming the labor-intensive methods, the incomplete data, and due to the access and the safety risks, and the need for enhanced analysis capabilities. So that includes the utilization of advanced technologies for that effective corrosion monitoring and mitigation. So what is corrosion under installation? CUI, as we like to call it. It's very simple. It's just that. Corrosion under installation is really just a severe form of corrosion that happens under your installation. There's a ton of different factors that come into play when understanding what causes CUI. There's temperature, there's humidity, marine-like environments, there's damage jacketing. The amount of damage jacketing that allows for water ingress is substantial. The highest incident of leaks in refineries and chemical plants are caused by CUI, not process corrosion. CUI is at times overlooked, but it's crazy to think that 40 to 60% of all of our maintenance costs are related to CUI leaks. So if you can cut that down, that's 40 to 60%. That's astronomical. If you can cut that number down, even by a third, even by half, that saves so much money in the long run that you can then put back into either other inspections or other programs. So managing it, preventing it, and detecting it. during the life cycle of an asset, it's imperative to regularly monitor and inspect pieces of equipment to verify their integrity. Non-destructive testing is crucial for comprehensive corrosion mapping, especially in this industry where in the oil and gas industry, we deal with materials that are highly corrosive by nature, and they're also flowing through pipes and equipment at extreme temperatures and pressures. So not only that, but most areas that we need to test cannot easily be shut down. So they're vital. If we shut down, we lose production, we lose money. It's not good. So we need to be able to utilize certain forms of non-destructive testing to avoid that and prevent that. And that's where these various methods of NDT give engineers an edge, and that edge being they can accurately pinpoint corrosion in real time without disrupting that system. So prevention and detection of CUI, it's crucial for mitigating risks and ensuring operational safety. A big one is inspection plugs. They're commonly used to check for CUI in areas that might be prone to corrosion. Utilizing these plugs or randomly removing insulation, that's another very common procedure out there, is just where we think there might be corrosion, strip the insulation and potentially find nothing. I can't tell you how many times I've heard from inspectors or asset owners or seen ourselves here. You can check with UT in an inspection plug, let's say at point A, and then 10, 15, 50 feet down the same line, you check another plug and they're perfectly fine. Great, okay, cool. The problem is the chances of it failing in between. And that's what we've seen a lot, is the incomplete data between points A and point D, where certain NDT methods can give you that holistic view and more comprehensive approach to understanding your pipe or equipment's integrity. So proactive measures, including that implementation of continuous scanning, coupled with the comprehensive data analysis, plays a vital role in safeguarding equipment from CUI and prolonging its operational lifespan. So in short, having a complete picture allows engineers to schedule maintenance when it's needed and only when it's needed. This enables a company to be able to allocate its resources in the most cost-efficient way. So again, it's the triage aspect, being able to understand where their problems are, and let's go plan and attack. I think now we can go into a little bit more pulse eddy current. So I'm going to hand it over to Donald, and we'll go from there.
Yeah, thank you, Tyler. Yeah, just we'll dive a little bit in the more technical point of view of what is the pulse eddy current. So the pulse eddy current is what we call the electromagnetic techniques that mainly assist to detect or to assess the remaining wall loss on the ferromagnetic component, so mainly the cast iron and carbon steel. This technique allows us to inspect through non-conductive covering, and that also includes what we call the water jacket or the cladding, so which is mainly composed of stainless steel, aluminum, and galvanized steel. And yeah, so for the corrosion under insulation, so this insulation can be composed of mainly any non-conductive material, so non-conductive and non-magnetic. So that includes a floor covering like tiles, concrete, wood, composite rat repair, coating, paints. It can also go through the external corrosion products like these cabin blisters. And the PEC can also be used in for underwater inspection. So it means that it can also go through the marine growth. So basically anything that is non-conductive and non-magnetic, the pulse eddy current is applicable. It is now including a few standards. So just a few examples for the SME BPVC, the ISO 20669, and the APR RP 583. So as Tyler mentioned, the PEC can be used in different situations. So we have access to different probe or different sensors. On the picture on the slide before, you saw single element sensors. We also have the array sensors, as you can see on this picture on the right-hand side. So in that case, the CUI can be assessed using the instrument called the lift, which is a high performance unit with offer high productivity, and it also includes software and for data and reporting analysis. And the PEC is now used in a wide range of industries. It includes, of course, the oil and gas, but also anything related to the fireproofing, tank floor, ship deck, ship hull also, and of course, all the underwater inspection. So the main principle of the PEC is, well, its name is also include the pulse eddy current. So we send a pulse to magnetize the component. Then we cut the pulse and we'll listen to the secondary magnetic field, so that is emitted by the component. And based on the signal that will be received by the probe, we will be able to assess the remaining wall thickness. So on the example on the right-hand side, you can see the red line there, which indicate or represent the nominal wall thickness of a component. And you can see the white line, which is like representative of the presence of a defect. So based on that change of the A scan or the signal, we are able to assess the remaining wall thickness. So through the years, we develop what we call the advanced analysis toolbox to help to address different situations. So the first one is the compensated wall thickness. It is basically used to assess undersized defect. So they're depending of the probe resolution or footprint. So a defect can be undersized or not. So if it is undersized, we can use this algorithm to bring back the sizing to plus or minus 10% of the nominal wall thickness, which is the accuracy of the lift. So in this example on the right-hand side, you can see on the top, this is the original C-scan. So the remaining wall thickness was sized at close to 70% of the remaining wall thickness. And after using this compensated wall thickness, we can see that we bring back the sizing to 30% of the remaining wall thickness. And you can see on the bottom right the validation with the UT measurement. So we were pretty close to the UT measurement. So the second tool is called the toe scan. So this one was mainly developed to assess different situations. So the first one is to help to discriminate if a defect is undersized or not. So in which case we can use the compensated wall thickness. And depending of the signal that we will get on this tool, we can assess the presence of corrosion products, mainly the scab. So since it is a corrosion under insulation, we don't have access to the surface. So this tool will help to identify the presence of scab and blisters. And one of the most important features of the toe scan is to help to evaluate the impact of the water jacket. So depending of the alloy, so mainly if it is aluminum, stainless steel, or galvanized steel, it will have some impact on the toe scan, and we will be able to evaluate this impact and to, let's say, validate if the component definition is matched the drawing or the technical drawing, for example. The most recent one is called the PERM tool, for permeability tool. So this one was developed to assess, I would say, an important point with the pulse current is the, I would say, to mitigate the number of false positive indication. So basically, this tool will help to discriminate a true or loss from false positive indication. And those false positive can be or can originate from a change of permeability, for example, caused by heat affected zones or the wells or interfering components. So through the years, we observe certain, I would say, behavior of the A scan and the C scan. So for a true or loss, for example, on your C scan, you will see a decrease of the wall thickness, but also at some point on the signal, we'll see a decrease of the amplitude. On the other hand, for a false positive indication, you will also see this decrease on your C scan, of course. But in that case, in most of the time, you will see an increase of the amplitude. So based on this correlation, we build or design a graphical tool, which is the perm tool, to help to discriminate the false positive from the true or loss. So with this feature, it's quite easy to distinguish the two indications. So back to you, Tyler.
Yeah, thanks, Donald. Moving on, I think now we'll kind of get into the integration piece of this type of technology, which has advanced quite drastically over even the last 5-10 years to how can we incorporate that into robotics and a solution to help in this industry when it comes to corrosion and CUI specifically. In today's rapidly evolving, technological landscape, robotics have emerged as a driving force behind this new era of innovation. So at its core, robotics refers to that integration of this cutting edge technology into various aspects of every industry globally. But what it's doing is revolutionizing the way inspections are performed and certain services are delivered. This transformative field combines the precision of engineering, which we see here, and working for a technology or robotics company I see every day. You combine that engineering with artificial intelligence, which leads to unprecedented levels of efficiency, productivity, accuracy, and of course, probably first and most priority would be the safety aspect. Utilizing robotics allows for that continuous data collection and analysis, which enables comprehensive corrosion assessment and proactive maintenance strategies. So it helps us make those decisions that are important as part of our inspection programs. Here are just a few of the robotic solutions out there that help with inspections. There's visual inspection robots, there's radiography, there's real-time radiography, ultrasonics, several different types of ultrasonics, pulse eddy current, as we're talking about today more specifically, and Donald was able to clearly help understand that. And then there's also infrared and some thermal robots as well. Those are just a few. So a combination of this artificial intelligence and data analytics means that these robots can aid in crucial decisions behind many of these asset integrity programs. So there's value today and improvements for tomorrow with any robotic solution. A few key benefits of these robotic inspection methods, or these crawlers, or I call it a crawler because that's what we do. But these robotic solutions, time and costs are greatly reduced. That's one of the easiest ones to talk about. So there's minimal or no need to erect scaffolding or take it down. It reduces the unnecessary stripping of insulation and removal of insulation. And quite frankly, robots allow and enable for more data per dollar spent. Another value add, of course, is the improved safety or the risk reduction. This is simple. Robots enhance the safety of workers by eliminating the exposure to risk. You can put a robot where you don't want to put a human. It circles back to what I was talking about earlier. It could be at heights, the confined spaces, the hazardous areas. Robots aren't affected, right? Humans can be. So it's very, very easy to reduce that risk and put us into that nice green box in our matrix versus having humans out there performing some of these inspections. And lastly, the quality of data collected utilizing robotics has been proven to be more reliable. Inspection robots can endlessly and tirelessly perform inspections day in and day out without fatigue or boredom that could impact their judgment or ability to collect data properly. That's just a human factor being eliminated. It is what it is. The robots don't get tired. We can get tired. Robotic inspections, in a nutshell, represent a paradigm shift that is reshaping these traditional methods and catalyzing the creation of these novel solutions to old age challenges that we're dealing with still to this day. Some of these plants, 50, 60 plus years old, and we've been stuck in that age for some time. And I think this different robotic solutions can help lead the future of this industry. So when it comes to the data being collected, Donald did a great job explaining some of the technical aspects of pulse eddy current, but utilizing PEC allows for an easy understanding of areas that could be concerning or could be problematic, where you need to then go follow up or do some further investigations or actions need to be taken. It drastically reduces the amount of unnecessary stripping. I've said it a few times, it's a big deal. That's the whole point, is being able to eliminate unnecessary auxiliary costs. So you can reduce the number of how much you have to unnecessarily strip. You can 3D, almost a digital twin in a sense. It enables a 3D reconstruction of your equipment. So you're able to overlay this data, so like a digital twin, which gives you that holistic view that you might not have had before with the way the data is displayed, like here on the screen. You can easily share it, you can easily view it, you can understand that data more so than spot checking or maybe 10,000 numbers in an Excel document. There's advanced analytics options as well that are also available, such as corrosion modeling, what-if scenario testing, and outlier characterization. So in conclusion, right now, there is no one-all be-all solution to robotics or CUI inspection, no silver bullet, so to speak. There are, however, companies actively researching, developing, and deploying more versatile and robust robots every single day. In an industry that is rightly obsessed with cost and risk, the use of robotics for inspections is a sensible, risk-savvy, and money-saving decision, to be quite frank. That's what companies like ourselves and Edify are working towards. So that's all I had. Thank you very much. I know we're about to get into some Q&A. We like to spend a little bit more time maybe answering some questions than reading off of a PowerPoint, but that's about it. Thank you very much.